Hello students, welcome to the video module on boundary conditions and uniqueness theorems. Before learning about uniqueness theorem, we are reviewing Poisson's equation. We know that the Gauss law states that del dot D equal to rho V, the volume charge density. We also learned D equals epsilon times E, the electric field. And also we know the relation connecting electric field and potential E equal to negative del V. So substituting for D in the first equation, that is the Gauss law equation, del dot epsilon E equal to rho. Also replacing E with negative del V. So we get del dot epsilon times negative gradient of potential equal to rho V. So this can be written as negative epsilon del square V equal to rho V. So that can be simplified to del square V equal to negative rho divided by epsilon. This is known as Poisson's equation. Del square V equal to minus rho divided by epsilon is Poisson's equation. Okay. Now, in a charge-free region, if the volume is devoid of free charges, if there is no volume charge density, then the Poisson's equation can be written as del square V equal to 0. This is known as the Laplace equation. Now, let us learn about the first uniqueness theorem. The first uniqueness theorem states the solution to Laplace equation in some volume V is uniquely determined if the potential V is specified on the boundary surface S. That means if the potential on the boundary is specified, then the potential over the entire volume can be determined or can be uniquely determined. So that is the statement. The solution to Laplace equation in some volume, this is a kind of V, so we are using this symbol for volume. Okay, so the solution to Laplace equation in some volume V is uniquely determined if the potential V is specified on the boundary surface S. So we can write the Laplace equation del square V equal to 0. This is the Laplace equation. So according to the first uniqueness theorem, if there is a solution to the Laplace equation on the surface, then the potential, the solution to the Laplace equation or the potential inside the volume can be specifically determined or uniquely determined. So there will be only one solution for Laplace equation in this entire volume. If the volume of, if the solution of Laplace equation is specified on its boundary, then the solution of Laplace equation inside the volume is uniquely determined. That means only one solution inside this volume. So how to prove this? In order to prove this, we can take the contradictory assumption statement rules. Like we can assume that there are two solutions to the Laplace equation. Let that be V1 and V2. So two solutions are there. So that del square V1 equal to 0, del square V2 equal to 0. Okay, so the uniqueness theorem states that there is only if the potential is defined specified on the boundary, then there is a unique value of potential inside the volume also. So in order to prove this, we are taking the alternate or contradictory statement. That means there are two potentials inside this volume, and later we prove that those two potentials are same, so that the final conclusion can be like there is only one potential inside. Okay, so we have to prove that V1 and V2 are same. So first we assume that there are two potentials inside the volume. That means there are two solutions. So we can write the Laplace equation del square V1 equal to 0 and del square V2 equal to 0. Okay, now we can define a potential V3 that is equal to V1 minus V2. So after all we have to prove that is V3 equal to 0. That is, if V3 equal to 0, then V1 will be equal to V2. So now we can write the Laplace equation for V3, that is del square V3 equal to del square V1 minus del square V2. This is equal to 0 because individually we know that del square V1 is 0 and del square V2 is 0. That means del square V1 minus del square V2 equal to 0. So we have del square V3 equal to del square V1 minus del square V2 equal to 0, because del square V1 is 0 and del square V2 is 0, then del square V3 is also 0. But that not concludes that V3 is 0. So, but we have got only the second derivative of V3 is 0, that is del square V3 is 0. Now we can apply the boundary conditions. So what is the boundary conditions here? On the boundary, V1 equal to V2, because the potential on the boundary is same. It must be same. If the potential on the boundary is not the same, then that means there is potential difference and charge flow occur on the conductor surface. Okay, so without connecting to any source, the charge flows or current occurs there. But in real practice, such a situation is not occurring. That means on the surface, V1 and V2, the potentials V1 and V2, these are same. This is the boundary conditions. On the boundary, the potential is uniquely determined. On the boundary, the Laplace equation has got only one solution. That means V1 and V2 are same. So on the boundary, V1 and V2 are same. That gives on the boundary V3 is equal to 0, because V1 and V2 are the same on boundary. That concludes, or that gives V3 is equal to 0 on boundary. Okay, now now we got an idea that V1 equal to V2 on the surface, or V3 equal to 0 on the boundary. So V3 is a solution to this Laplace equation, del square V3 equal to 0. The solution is V3, and we know that that value V3 is equal to 0 on the boundary. But now, the according as per the definition, the Laplace equation has an extrema. That means a maxima or minima on the boundary. Nowhere else inside the volume. So what is that? A Laplace equation gives a condition that the potential has, or V3 has, a maximum value or minimum value, the extremum value on the surface. So the maximum or minimum value of V3 is on the surface, and from this we already got that answer. V3 is equal to 0. That means the extremum value of V3 is 0. So its maximum value is 0 and its minimum value is 0. That means, what is the value of V1 and V3 inside? Inside also it is 0. So V3 is 0 inside also, because its extremum values on the boundary are 0. V3 is equal to 0. It has a value 0. It has a minimum value 0. It has a maximum value 0. That means there is no other value for V3 inside the conductor also. If V3 is equal to 0, the minimum one, and V3 is equal to 0, the maximum one, that shows that what is the values in between. Everywhere it is 0. That means the value of V3 is 0 inside the conductor. So if V3 is 0 inside the conductor, then what it shows? It shows that because V3 is actually V1 minus V2. That is the definition that we give. So V3, if V3 is equal to 0 everywhere inside the conductor, that shows V1 is equal to V2, or there is only one potential, or there's only one solution to this Laplace equation. So if the potential on the surface is unique, if the potential on the surface is defined, then the potential inside is uniquely determined, can be uniquely determined. That is the sole meaning of the first uniqueness theorem. Or we can say that first uniqueness theorem, or the uniqueness theorem, is a license to imagine. So just if we know the potential on the surface of the conductor, then we can imagine that the potential inside the conductor also the same. There's only one unique solution to the Laplace equation. There's only one unique potential everywhere. That is the sole meaning of first uniqueness theorem. If you know the potential on the surface, that same will be the potential inside also. So let us consider this example. So here you can see that a cavity inside a metallic volume. So show that volume is constant inside the cavity. That is what we have to prove. So we can use the first uniqueness theorem to prove this. So you can see that here everywhere this is the metal volume. All these are metal volume, and inside is the cavity. So this is the cavity, and this is metal. So we know that the potential inside, so if the potential on this cavity surface is V, so let it be V naught. If that is V naught, then the potential inside, that also will be V naught. So we just define it as V. So V equal to V naught according to the first uniqueness theorem. If the value of potential is defined on the surface, then the same will be, or the potential inside can be uniquely determined. That is, that will be same as that of what are the potential on the surface. There is no potential difference in that. So this is the advantage of first uniqueness theorem. So mere imagination of the value, because we already proved why it is so. So if you know the potential on the surface, then we can find the potential inside that also. So this we already proved with the help of electric field, because we know that inside the cavity the electric field is zero, and the electric field is equal to the negative gradient of potential. Right. So or E equal to negative del V. So if electric field is zero, that means 0 equal to negative del V, or V value is a constant. That means whatever value on the surface, that is equal to inside also. So that is another way we proved that one. But we can prove that by merely applying the first uniqueness theorem also. Okay, this is one of the application of first uniqueness theorem. Okay. The same argument of uniqueness theorem can be used for Poisson's equations also. The only change that we made here is that we throw some charges to the volume, so that the equation becomes del square V equal to negative rho divided by epsilon 0, rho V divided by epsilon 0. So here also we have to, so this is that surface. So here also we have to prove that if the potential on the surface is defined, specifically defined, then we can uniquely determine the potential inside also. So the same type of derivation for this Poisson's equation also we can use. So let us imagine that there are two potentials inside the volume. So that obeys Poisson's equation, del square V1 equal to negative 1 rho over epsilon 0, and del square V2 equal to negative rho over epsilon 0. So now we can define another, we can define V3, which is equal to V1 minus V2. So we can apply the Poisson's equation, del square V3 equal to del square V1 minus del square V2, that is equal to minus 1 over epsilon 0 rho plus 1 over epsilon 0 rho, that gives 0. So that means del square V3 equal to 0. Now we can apply the boundary condition. What is the boundary condition? On the surface, V1 equal to V2 on boundary. That means V3 equal to 0 on boundary. So now we are applying the condition of Poisson's equation is that this equation allows no extremum values inside the volume, or the extremum value occurs on the surface. That means minima or maxima value occur on the surface. So the maxima or minima of V3 is on the surface, and we know that that is 0. If the minima is 0, maxima is 0, then everywhere inside also the value of V3 will be 0. So if V3 is 0 everywhere, that means V1 minus V2 equal to 0. Or we can say everywhere inside the volume V1 equal to V2. So the potential inside the volume is uniquely determined. That is V1 equal to V2, and that will be same as that of the value on the surface. Okay, this is the first uniqueness theorem applied to Poisson's equation also. Now we will learn about the second uniqueness theorem. The second uniqueness theorem states that in a volume surrounded by conductors and containing specific charge density rho, the electric field is uniquely determined if total charge on each conductor is given. That means if the total charge in a conductor is given, then the electric field is uniquely determined. There is only one electric field. Okay, so let us prove this second uniqueness theorem. So for that, here also we can adapt the same type of technique that we employed for the first uniqueness theorem. So here also we assume that there are two electric field present inside the conductor, that is E1 and E2. Two electric field E1 and E2 are present, and so that E3 is equal to E1 minus E2. Now applying Gauss law, we can write delta del dot E1 equal to rho over epsilon 0, del dot E2 equal to 1 rho over epsilon 0. We can write this in integral form, integral E dot dA equal to 1 over epsilon 0 Qi, or over a surface, ith surface. For an ith surface, it is integral E1 dot dA is equal to 1 over epsilon 0 Qi. The Qi is the total charge in that surface, and E2 dot integral surface integral E dot d is equal to 1 over epsilon 0 Qi. Now, the for the entire surface, if we consider instead of ith surface, we are considering the total surface. Then the total outer when we are doing that for the outer boundary, we can write surface integral about the outer boundary is equal to E1 dot d is equal to 1 over epsilon 0 Q total, the total charge enclosed by the surface, and integral E2 dot d is equal to 1 over epsilon 0 Q total. Now we know that the electric field E3 is equal to E1 minus E2. So when you find del dot E3 is equal to 0. So in the region between the conductors, we can write integral E3 dot d is equal to 0. So this is written in the integral form, integral E3 dot d is equal to 0. Now we are over each, so that means integral E3 dot d is equal to 0 over each boundary surface. Okay. Now we can write del dot V3 E3 is equal to V3 times del dot E3 plus E3 dot del V3. You can see these rules at the start of our text. Okay, so del dot V3 E3 equal to V3 del dot E3 plus E3 dot del V3. Okay, that can be written as, you see the first term here, this term del dot E3, that is 0, so that gone. Then E dot del V3, we know that E3 is a negative gradient of del V3, so we can substitute that here. So instead of del V3 we can substitute minus E3, so there's already an E3, so E3 times E3, E3 square, that is why the answer is minus E3 square. So del dot V3 E3 can be written as minus E3 square. Now integrating both sides, that is we are going to integrate on this side and integrate on this side, so we are integrating on both sides over the volume V. So this is what, so we are integrating over the volume V, and this is the right side. But the left side, we can convert the volume integral into surface integral. So in volume integral del dot V3 E3 d tau can be written as surface integral V3 E3 dot dA. Okay, so we applied the rule and we can convert the volume integral into surface integral. And this is the RHS. And this is the LHS. And it is converted to this form. Okay. And we know that. So what is this E3 dot dA? That we already know that it is 0. So this term becomes 0. That shows E3 square d tau over the volume is equal to 0. So this shows that E3 is equal to 0. If E3 is equal to 0, we can write E1 minus E2 is equal to 0. That is E1 equal to E2. That shows that there's only one electric field present. If the charges are specifically given, there's only one electric field or unique electric field is present inside the conductor. So hence the second uniqueness theorem is also proved. Thank you, students.